For years, email gateways and desktop scanners have prioritized the detection of raw executable files. This has forced a tactical shift. The once obvious threat is now shattering into a fleet of innocuous document icons designed to blend into the daily flow of office work. This evolution means you don't always have to click a download button to get infected. Simply visiting a compromised legitimate website can trigger a silent infection sequence known as a drive-by download. This flowchart illustrates the mechanics. When your browser connects to the site, a hidden iframe silently reroutes your traffic to an exploit kit server. This server instantly fingerprints your system, identifies your specific browser version and plugins, and delivers a vulnerability payload custom-built for your machine's weaknesses. Because this entire sequence happens in the background without a single user prompt, everyday web browsing effectively becomes a hidden minefield. But many scripts ensure their exploit code executes successfully after a browser crash. Attackers use heap spraying. They flood the browser's memory allocator with controlled data, filling the heap with massive blocks of code to guarantee the processor lands exactly on their malicious payload. To hide that payload from scanners, attackers use JavaScript obfuscation, wrapping the logic in multiple layers of encryption. However, the browser must eventually run that code. To do so, it must pass the decoded string to an execution command like eval. Looking at this split screen, you can see how an analyst turns the script's requirements against it. By overriding the eval function with console.log, the browser is forced to safely print the decoded readable payload into the console on the right, instead of executing it. But many scripts employ environmental keying to protect themselves. The malware checks for a specific corporate domain or system marker. If it doesn't find the exact target environment, it exits silently, leaving the analyst with nothing but an empty script. These scripts operate with a layer of awareness, probing for any sign of scrutiny. To reach the actual payload, the analyst must move with precision, systematically bypassing each defensive check without triggering the script's self-termination. This 3D blueprint breaks a standard PDF into 4 structural layers: header, body, cross-reference table, and trailer. Moving into the body layer, attackers weaponize highlighted object blocks by embedding trigger tags like /OpenAction and /JavaScript, forcing the reader to execute code automatically. Automated security scanners are often blinded by stacking compression layers like /decode. To see the threat, an analyst must manually peel back each filter layer to decompress the hidden data. Attackers also construct polyglot files, which are engineered to be valid as 2 different formats, such as a file that is both a valid PDF and a valid zip archive, allowing it to bypass scanners that only look for one specific file type. This reveals that a trusted PDF is not a static document, but a complex, programmable container capable of hiding entirely separate architectures and logic systems. With RTF files, attackers alternate between abusing legitimate design features, like launching embedded objects, and exploiting memory corruption vulnerabilities in legacy components. A common target is the legacy Microsoft equation editor. It contains a memory vulnerability that allows attackers to achieve code execution through standard-looking RTF files. To find the payload, analysts use tools like rtfdump.py to isolate the specific malicious data stream hidden from the user's view. This technical view shows the assembly instructions, like MOV and JMP, that comprise the extracted shellcode. By loading this into a debugger, analysts can safely trace the execution path and identify exactly what the malware intends to do to the system. These legacy features, buried within decades-old formats, provide attackers with a permanent attack surface that exists beneath the level of standard security patches. Within the enterprise, Microsoft Office documents are the primary delivery vehicle for malware, traditionally relying on weaponized VBA macros to initiate a network compromise. To evade signature-based antivirus, attackers use string concatenation, breaking up a suspicious command into harmless-looking fragments that are only joined together when the macro executes. Notice the contrast here between standard VBA script and this block of compiled hexadecimal P code. Attackers can strip away the human-readable source code entirely, leaving only the P code for the macro engine to execute. As VBA defenses improve, some attackers are reverting to legacy XL 4.0 macros, using an older architecture to bypass modern security controls designed specifically for VBA. This demonstrates that analyzing source code is insufficient when the application's execution engine can be tricked into running a hidden, parallel language. But attackers have adapted to environments where all Office macros are disabled by default. Techniques like remote template injection allow a document to dynamically pull malicious code from an external server via the settings.xml.rels file, bypassing the need for embedded macros entirely. More recently, secondary payloads are being hidden inside embedded objects within Microsoft OneNote files, relying on a simple user click to trigger the infection. Ultimately, the security of a network relies on the rigorous forensic deconstruction of these everyday files. By identifying and neutralizing malicious logic before it executes, analysts outsmart the software we trust and protect the systems we use every day.